I'd like to thank the organizers for the opportunity to speak here. So my talk is going to be on a certain Hecke algebra isomorphism of Kazhdan. This mostly concerns representation theory of p-adic groups. I'll review most of the things that are needed for this talk. Okay, so I'll begin with stating the Kazhdan isomorphism, and then this isomorphism has some applications to the local Langland's correspondence. So I will review the local class field theory and the local Langland's correspondence, and the application of this theory to to those conjectures. And finally, I'll talk about generalizing this theory to non-split groups. Kazhdan isomorphism is a priori known only for split groups. So I will talk about its generalization to non-split groups. So we'll fix some notation. We'll work with non-Archimedean local fields with finite residue fields. So these are either finite extensions of QP, these are the fields of characteristic 0, or they are isomorphic to FQ of T, the field of Laurent series in one variable with coefficients in FQ. These are the non-Archimedean local fields of positive characteristic. So, and we'll be working with smooth representations of G of F. I'll just quickly recall the definition. So let G be a connected reductive group over F. A smooth representation of G of F is pair sigma V, where V is a complex vector space, and every vector in V is fixed by a compact open subgroup of G of F. That's what it means for the representation to be smooth. And it is admissible if this space, that is the set of all vectors that are fixed by this compact open subgroup K, this space is Vk. If this is finite dimensional, then this representation is called admissible. Okay, so we'll be basically working with irreducible admissible representations of this connected reductive group, of the F points of this connected reductive group G of F. Okay, so I'll go ahead and state the Kazhdan isomorphism. So this is basically a theory for split connected reductive groups. Some examples to keep in mind are GLN, GSP4 or SO2n plus 1. And let Km be the kernel. Recall that G is defined over Z, so you can look at G of R for any ring R. So I'm looking at Km. I'm defining Km to be the kernel from G of OF to G of OF mod PF to the M. This is the usual mth congruent subgroup of G of OF. Then this Hecke algebra is the C-span of these characteristic functions, where you look at the double cosets of Km in G of F, and you look at the characteristic functions of these double cosets. Normalize, there's a Haar measure, normalize with respect to a fixed Haar measure, and this is the Hecke algebra H of G of F with Km. So this basically contains functions that are both left and right invariant with respect to Km. And this is an algebra with respect to convolution. Okay? So why is this of relevance in the representation theory of p-adic groups? Given an irreducible representation, you can look at this space Vkm. This is a simple, if the representation is irreducible, and if this space is, we'll say it is non-zero, it becomes a simple H of GKM module. And more generally, the functor that takes a representation to its Km fixed vectors is an equivalence of categories between the category of representations of G of F that are generated by their Km fixed vectors and the category of modules over H of GKM. This is only true when you're working with complex representations, but we still have this equivalence of categories. In particular, if you know this module Vkm, then you can actually recover the representation itself. So this Hecke algebra is of interest in the context of representations of p-adic groups. So the Hecke algebra isomorphism of Kazhdan that I alluded to is basically about this Hecke algebra. So Kazhdan proved that this Hecke algebra is essentially can be compared over fields that are sufficiently close. I'll define what close fields are. So these are, I'll define what close local fields are. So let M be an integer greater than or equal to 1. Two non-Archimedean local fields F and F prime are M close if these quotient rings are isomorphic. OF mod PF to the M and OF prime mod PF prime to the M are isomorphic. So an example of this is this field Fp of T and Qp of P to the 1 over M are M close. Note that this is a field of positive characteristic and this is a field of characteristic 0. And to see this, you can just look at, I'll just quickly say how one shows this. Zp of P to the 1 over M mod P is isomorphic to this ring. Zp of x mod x to the M minus P And you're also killing off P, which is Fp of x mod x to the m, which is this. So these two fields are M closed, one being a field of positive and other being a field of characteristic 0. More generally, it is easy, just from this, it is easy to see that given a local field of characteristic P and an integer, you can choose a local field of characteristic 0 that is M close to F. So you just have to choose this field of characteristic 0 to be ramified enough so that in this quotient you're killing off P. That is all you have to do. So given a field of characteristic P, you can also always find, and an M, you can always find a field of characteristic 0 that is M close to it. Now the Kazhdan isomorphism, so I'll state what the Kazhdan isomorphism is. Recall, as I mentioned earlier, this was a priori only for split reductive groups. So I'll fix a split connected reductive group. So I can fix a model for it over Z and let Km be the kernel from G of OF to G of OF mod PF to the M, and I'm considering this Hecke algebra. Recall that this is spanned by the characteristic functions of all the Km double cosets in G of F. And it is an algebra with respect to convolution. Now, it is easy to see that if the fields F and F prime are M close, then these two quotients are isomorphic, right? Because both of them are so this is isomorphic to G of OF mod PF to the M. But the ring, if the fields are M close, then those two rings are isomorphic, OF mod PF to the M and OF prime mod PF prime to the M. So these two groups are isomorphic. The theorem of Kazhdan is the following. Let F be a non-Archimedean local field and M greater than or equal to 1. There exists an L greater than L. There exists an L which is larger than M, which may be larger than M, but at least as large as M, such that for any local field F prime that is L close to F, the Hecke algebras at level M become isomorphic. Okay, so this theory allows you to compare the Hecke algebras of one over a field of characteristic 0 and other over a field of characteristic P. And as I said, the representations of periodic groups are closely related to modules over these Hecke algebras. So in particular, the Kazhdan isomorphism will allow you to compare representations of periodic groups in positive characteristic with the corresponding representation theory in characteristic 0. So I'll state this more precisely. This one is M. So you have to assume that the fields are closer to get an isomorphism at level M. L is larger than M, so the fields are L close. In particular, they're also M close. So in fact, one can prove that these are isomorphic as complex vector spaces when the fields are just M close. This is a consequence of the Cartan decomposition, which I'll state later. But to prove that this is an algebra isomorphism, one has to assume that the fields are closer. So yeah, L is greater than or equal to M. It was a conjecture of Kazhdan that L can be chosen equal to M, and it can be proven now. So, but I won't get into that in the talk. But you can take L equals M. Okay. An irreducible, an irreducible representation becomes a simple H of G Km module when you take the Km invariant vectors. So in particular, if the fields are sufficiently close, then the Kazhdan isomorphism gives a bijection between the representations of G of F with non-zero Km fixed vectors and the representations of G of F prime with non-zero Km prime fixed vectors. As I said, this isomorphism has proved helpful in studying the local Langland's conjectures in positive characteristic via the corresponding theory in characteristic 0. So I will I will quickly recall at least the statement of the local Langland's conjectures in a specific setting, and I will also motivate these conjectures. So I want to state the main theorem of local class field theory. So recall that you have, so F1, so this is an exact sequence that I'm looking at. F is a non-Archimedean local field. I have fixed a separable closure F bar of F. And this is the maximal unramified extension of F. Then this fits into this exact sequence. Recall that this is isomorphic to the profinite completion of Z. Yeah, this is the maximal unramified extension of F contained in the separable closure, and it's isomorphic to the profinite completion of Z. And inside this, Z sits as a dense subgroup, and the Weil group is the inverse image of Z in the Galois group of F bar over F. It fits into this exact sequence. This is the definition of the Weil group. Okay? And WF is called the Weil group of F, and this group is called the inertia group of F. So you've gone mod the maximal unramified extension of F. So the rest of it, any finite extension of F1 is totally ramified, and this is called the inertia group of F. Now, the main theorem of local class field theory is basically a study of finite abelian extensions of a local field. So this theorem gives a topological isomorphism between F cross and the abelianization of the Weil group, and this induces an isomorphism when you pass to the profinite completions between F, the profinite completion of F cross, and the abelianization of the absolute Galois group. Here, F cross hat is OF cross Z hat, the profinite completion of F cross. And recall that once you fix an uniformizer, you have an isomorphism like this between F cross and OF cross Z. So the main theorem of local class field theory basically gives you an isomorphism between F cross and the abelianization of the Weil group. Now, if you want to translate this into, say, representation theory of GL1F, because F cross is GL1F, what this, before that I want to say a little bit about the depth preservation. Okay, so the inertia group admits a nice descending filtration with respect to upper numbering, and this isomorphism of local class field theory respects this upper numbering filtration in the sense that the units in F cross maps to the abelianization of the inertia group, and these filtration 1 plus PF to the M maps to the mth upper numbering filtration of the inertia abelianized. So local class field theory basically gives you an isomorphism from F, if you look at continuous homomorphisms from F cross to C cross, then via the isomorphism of local class field theory, you have a, this is isomorphic to homomorphisms from the abelianization of WF to C cross, but C cross being abelian, this is just homs from WF to C cross. So local class field theory basically allows you to compare characters of F cross with characters of WF. Now, the local Langland's correspondence can be seen as a vast generalization of this one-dimensional version of class field theory. So, I'll say just for GLN, this is Hom from GL1F to C cross. You replace it with irreducible smooth representations of GLNF, and Hom from WF to C cross with semisimple n-dimensional representations of WDF. I will say why one needs WDF and why the Weil group is not enough. Here WDF is the Weil-Deligne group of F, which is WF cross SL2C. So first, for an irreducible representation of WF is a pair phi V, where dimension of V is n, and every vector has open stabilizer in WF. This is something we saw earlier also. It is irreducible if it does not have any proper WF invariant subspaces, and it is semisimple if it is a sum of its irreducible subspaces. Now I have to explain why one, I'll just briefly explain why one needs to, so in here we replaced WF with representations of the Weil-Deligne group. I will say briefly what one possible motivation for that is. So So the local Langland's correspondence is basically a bijection between representations of irreducible smooth representations of GL and F with the semisimple representations of WDF. Why WDF? To establish this bijection, it turns out that the semisimple representations of WF are not enough to account for all the irreducible representations of GL and F. We need to expand this. So one issue is one can look at parabolic induction. I have said what it is, but you can do a parabolic induction. You can fix a representation of a Levy subgroup of GL and F, which is of this form, inflate it to the parabolic and induce it to GL and F. This representation is not always irreducible, and to account for the summands of these representations, one has to go to the this larger group of which is the Weil-Deligne group. Now, with this very vague motivation, let me just state the local Langland's correspondence for GLN. It is a bijection between irreducible smooth representations of GL and F with the semisimple n-dimensional representations of WDF with sigma going to phi sigma. When one says that this is a bijection, one would like to know, one would like to characterize this bijection. So it is characterized in the following manner. There is a theory of L and epsilon factors for representations of p-adic groups, which is due to Jackie, Peditsky, Shapiro, and Shalaika. So there is so given a representation of GLN and a representation of GLT, for one can associate a theory of L and epsilon factors. Here is I is an additive character, and there is a similar theory for representations of WDF, which is due to Artin, Deligne, and Langland's. Here I'm looking at the tensor product of phi sigma and phi tau, and the local Langland's conjecture. The local Langland's correspondence is supposed to preserve these invariants, the L and epsilon factors, and in fact, it is a unique map that is characterized by this property. So this for GLN was known over local function fields in positive. It was first done in positive characteristic in '93, and later it was done in characteristic 0 due to Harris-Taylor and Henia, and more recently by Scholze has given a different and a more a different proof of this correspondence in characteristic 0. So then beyond GLN, what can one say beyond GLN? For I'll still work with split reductive groups. For other split reductive groups, the local Langland's correspondence is no longer a bijection. It's only a surjective finite to one map, and it partitions the space of irreducible representations of G of f into what are called L packets, and there is a way to parameterize representations in a given L packet. But here I work with irreducible smooth representations of G of f. Here one has to look at homomorphisms phi from WDF to LG. This is the Langland's dual group of G. When the group is split, the Langland's dual group is just the complex group with the dual root datum. So for GLNF, it was GLNC. And the correct analog for that for general connected reductive groups is one works with the Langland's dual group. And because I'm assuming that the group is split, this is just the complex group with the dual root datum. Otherwise, I have to take care of a Galois action. This group is larger than the complex group with the dual root datum. And this has been established for GSP4. This was due to Gan and Takeda in characteristic 0. And I looked at this question in my thesis in characteristic P. And the method was to use the method of closed local fields in this theory of Kazhdan. And similarly, for classical groups, this was known, this is due to Arthur in characteristic 0. And for split classical groups, it was joint work with Sandeep Verma in sufficiently large characteristic. So the Kazhdan isomorphism was used to study the Langland's conjectures in positive characteristic via the corresponding theory in characteristic 0. So that is one of the motivations of studying the Kazhdan isomorphism and also trying to obtain a generalization of it to non-split groups. Okay, but when I say, so the Kazhdan isomorphism will allow you to compare representations of G of f over closed local fields. But the Langland's correspondence is a bijection between representations of G of f and homomorphisms from WDF. So we need a corresponding theory on this side, which will allow you to compare representations of WDF over closed local fields. This is due to Deligne, I will recall that. So I'll use this notation consistently. Given an object associated to a field f, for the corresponding object over f prime, I will use the notation x prime. So f bar, I'll fix a separable closure of f. IF is the inertia group. We looked at these things earlier, but IF to the m is the mth higher ramification subgroup of IF with upper numbering. And the theorem of Deligne is the following. If the fields f and f prime are m close, then the Galois group of f bar over f mod IF to the m is isomorphic to the corresponding Galois group over the other field modulo IF prime to the m. So the Deligne isomorphism, on the one hand, it will allow you to compare representations of the Galois group over closed local fields, but it already but one of the results of Deligne already lays the foundation for the question we had asked earlier. The Deligne isomorphism is compatible with local class field theory. What do we mean by that? If the fields f and f prime are m close, then the Deligne isomorphism will give you an isomorphism between these two Galois groups, and you can pass to the Abelinaizations. As I said earlier, local class field theory was an isomorphism. The local class field theory was basically an isomorphism between the Galois group of f bar over f abelianized with the profinite completion of f cross, and I also indicated there that it preserves the filtration. So this is just the isomorphism of local class field theory. You have a similar theory over the other field f prime. And this is the Deligne isomorphism, and this is just the isomorphism of closed local fields. Here to recall, if the fields are M closed, then OF mod PF to the M is isomorphic to the corresponding ring over the other field. So you can take the units. So OF cross mod 1 plus PF to the M will be isomorphic to OF cross mod 1 plus to PF to the M for the other field, and you make a choice of uniformizers to get this isomorphism. So yeah, in the above, if the fields are M closed, then we have this isomorphism. This involves a choice of uniformizer. In any case, so the Deligne isomorphism is compatible with local class field theory. So the question that we, and also Deligne isomorphism allows you to compare representations of the Galois group. I'll just say that more precisely. So if you have a representation of the Galois group, an irreducible n-dimensional representation, which is trivial on IF to the M, then it factors through this quotient, and we have an isomorphism if the fields are M closed between these two Galois groups. So you get a representation of the Galois group over the other field. So in particular, the Deligne isomorphism gives a bijection between the isomorphism classes of representations of Galois group of F bar over F that are trivial on IF to the M and the corresponding set of representations over the other field. And okay, I don't know. Yeah, so and this remains true when the Galois group of F bar over F is replaced by the Weil group or the Weil-Deligne group. So the Deligne's theory allows you to compare representations over closed fields on the other side of the Langland's correspondence. Basically, it allows you to compare representations of the Galois group or the Weil group or the Weil-Deligne group. Now, I'll just summarize because we have said, I'll just summarize everything. So Deligne's result allows us to compare representations of the Galois group over closed local fields. Kazhdan's result and its variant, which I will not get into, in fact, Kazhdan's result enables us to compare representations of p-adic groups over closed local fields. And as I said, given a local field of characteristic P, there exists a local field of characteristic 0 that is M close to it. Given a local field of characteristic P and an M, we can always find a local field of characteristic 0 that is M. Now, is the Deligne-Kazhdan philosophy compatible with the local Langland's correspondence is the question. The one-dimensional version of this question is already Deligne's work, which I had recalled earlier, because the local Langland's correspondence in one dimension is just local class field theory. So to make this question more precise, assume that the fields F and F prime are sufficiently close, and we will consider the following diagram. If the depth of a representation on this side is defined via what are called these Moy-Prasad filtration subgroups. So instead of going into the definition of that, let me just make this simple observation. If the depth of sigma is less than M, then sigma has a non-zero km plus 1 fixed vector. It is easy to prove this. And similarly, if the depth of phi is less than M, then phi restricted to the mth upper numbering filtration of the inertia is trivial. So this puts us in the context of the Deligne-Kazhdan philosophy. So Kazhdan isomorphism, if you look at it at level M plus 1, it allows you to compare representations of G of F with depth less than M and representations of G of F prime with depth less than M, because both of them have non-zero km plus 1 fixed vectors, and that is what they become. So this will become a simple H of G km plus 1 module, and you have a Hecke algebra isomorphism. Similarly, if phi restricted to IF to the M is trivial, then the Deligne isomorphism will allow you to compare representations of the Weil-Deligne group. I'm calling representations, but when one is working beyond GLN, we have to look at admissible homomorphisms from WDF to LG. So I'll just think of G as GLN. Okay. So then the question is this diagram commutative? And this is exactly the one, in the one-dimensional case, this is exactly Deligne's result. Is this diagram commutative for groups like GLN, GSP4, or for classical groups? I have chosen all of them to be split classical groups, but that is because we are a priori only working with the Kazhdan isomorphism is for split groups. Okay, so so one can show that this diagram is commutative for GLN. This was part of my thesis, but it was also independently done by Aubert, Bob, Plyman, and Solowelt. And for GSP4, as I said in my thesis, we were able to prove that, in fact, we were able to prove the local Langland's correspondence for GSP4F in positive characteristic via the theory in characteristic 0. So you start with the representation of G of F in positive characteristic with depth less than M. Kazhdan will give you a representation in characteristic 0. Take its image under the local Langland's correspondence and pull it back up via the Deligne isomorphism. This will give you this will allow you to define this map in positive characteristic via the theory in characteristic 0, and one can prove that it has all the required properties, meaning it preserves the L and epsilon factors of pairs, and it is the unique map that is characterized by this property. And for split classical groups, this was joint work with Sandeep Verma. So this is sort of the motivation, one motivation to generalize the Kazhdan isomorphism to non-split groups. Not just in the context of Langland's correspondence, but it can be helpful in understanding representation theory of reductive p-adic groups in positive characteristic via the corresponding theory in characteristic 0. Okay. So as I said, there are essentially 3 key ingredients in the proof of the Kazhdan isomorphism. So recall, I have fixed a split connected reductive group over Z. Km is the mth filtration subgroup of G of OF. And if the fields F and F prime are sufficiently close, then Kazhdan's result tells you this, that these two Hecke algebras are isomorphic. There are essentially 3 key ingredients that one can pull out from this proof that are crucial. One is that this Hecke algebra is finitely presented. This is true fairly generally. It just follows, one shows that this Hecke algebra is a module of finite type over its center, and the center is a finitely generated C algebra. So this Hecke algebra is finitely presented. The group G of F admits what is called a Cartan decomposition. So if you look at the double cosets of G of OF in G of F, it can be described via this quotient where T is a maximal Z split torus in G, X lower star T is its co-character lattice, and W of GT is the Weil group of T is the Weil group of T in G. So in some sense, loosely let me say how this isomorphism works. So this object is more or less field independent. So what I want to do is go mod Km further on both sides, right? But G of OF mod Km is isomorphic to the corresponding group over the other field. So just using the Cartan decomposition and this fact, G of OF mod Km is isomorphic to G of OF prime mod Km prime. These two facts combined will already allow you to construct a vector space isomorphism between these two Hecke algebras. The point is, it is also an algebra isomorphism, and one has to use the fact that it is finitely presented, which is where you basically want these relations also to be respected. And that is where you assume that the fields are a few levels closer, just to prove that this is an algebra isomorphism, and you crucially use the fact that this Hecke algebra is finitely presented there. Okay, so if one wants to generalize this isomorphism to non-split groups, there are some questions that naturally come up. One, when the group is split over Z, one can work with this group over an arbitrary field after base change. You can just take the G of F points for any field F when the group is defined over Z. More generally, given a connected reductive group over F, we need to understand what it means to give a corresponding group over F prime. Right? If the group is actually defined over F and not over Z, we need to make sense of what it means to give a group G prime over F prime, where F prime is suitably close to F. And assuming this can be done, we need to understand the analogues of G naught of OF. Again, when G is defined over Z, this makes sense without there is no ambiguity here. So we need to understand what the analogues of K and Km are. And we need to prove this isomorphism. And recall that this is more or less obvious when the group is defined over Z. But this is not the case when we work with general connected reductive groups. So we need to prove this isomorphism, that K mod Km is isomorphic to K prime mod Km prime when the fields are sufficiently close. And finally, generalize the proof of Kazhdan to get the isomorphism at the level of Hecke algebras for the group G and G prime. Now, this question can be done generally. Given a group over F, one can make sense of what it means to give a group G prime over F prime. Loosely, to give a connected deductive group over F, you give a split group and you give an element of H1, right? So giving a split group over Z already makes one, so takes care of this, and you want to choose the same form. So when you make a so we prove a comparison theorem of the pointed sets H of the H1s and compare and make precise what it means to give a group G prime over F prime. So I will just explain how this is done for quasi-split groups. It can be done more generally, but so let R delta be a based root datum. I have fixed a split connected reductive group. T naught is a Z torus. A maximal split Z torus, B naught is a Borel, and I have picked fixed a pinning U alpha, which is an isomorphism from GA to the root subgroup, U alpha for the root alpha, and let EQS of F G naught sub M be the F isomorphism classes of quasi-split groups G that split and become isomorphic to G naught over an at most M ramified extension of F. By that I mean that the mth upper numbering filtration of the inertia is trivial. Okay, so I am basically looking at all the forms, outer forms of G naught that split and become isomorphic to G naught over an at most M ramified extension. Then this is what I was alluding to when I said H1. So this is parameterized by this pointed set H1 of gamma F mod IF to the M with values in aught of R delta. Okay, this is more or less a field independent object, and these groups are isomorphic provided the fields F and F prime are M close. Yeah, so this gives so the Deligne isomorphism will immediately give you a bijection between these two sets. Basically because it's parameterized by this H1. This is a field independent object. It was attached to us, this data. And these Galois groups are isomorphic if the fields are sufficiently close. So the Deligne isomorphism allows you to, given a quasi-split group over F that splits and become isomorphic to G naught over an at most M ramified extension, one can produce a quasi-split group over F prime that splits and become isomorphic to G naught over an at most M ramified extension. Okay, so this is what we mean by given a connected deductive group over F. What does it mean to give a group G prime over F prime? This is the more precise statement. Now, I will say a few words about the three ingredients in the proof of the Kazhdan isomorphism. This Hecke algebra is finitely presented as a fairly general result. As I said, it just follows by showing that this is a module of finite type over its center, and the center is a finitely generated C algebra. And the group G of F, this Cartan decomposition that we were looking at, this was proved in the work of Haynes and Rostami. So here, G is a connected reductive group, and K is a special maximal parahoric subgroup of G of F. This definition will involve looking at the Brouhatitz building of G of F. I will say just a few words about it later, but there is an analog of G of OF, which is this special maximal parahoric. And the analog of this Cartan decomposition was established by Haynes and Rostami. And as I said, the other ingredient is if the fields are M closed, then these quotients are isomorphic. But when the group is not split, this is not obvious because G is not no longer defined over Z, and what does it mean to choose a model over Z already becomes a question that needs to be addressed. Okay, it has been established for a pair GM, where G is a connected reductive group and PM is the mth Moy-Prasad filtration subgroup of the parahoric subgroup of G of F, of any parahoric subgroup of G of F. Now, with these, one just follows the proof of Kazhdan with minor modifications and can prove that if the fields F and F prime are sufficiently close, then these two Hecke algebras are isomorphic. Where here, G is a connected reductive group over F, Km is the mth kernel of this. So K was a special maximal parahoric subgroup of G of F, and Brouhatitz proved that they have underlying smooth affine group schemes with this K has generic fiber G, and its O points exactly gives you the paraheuric subgroup that you started with. So they constructed such group schemes, and we look at the kernel of this map, and this result will basically prove that K mod Km is isomorphic to K prime mod Km prime. And then one essentially follows the strategy of Kazhdan to get this result for general connected reductive groups. I will say just a few words. It may not help if one has not seen Brouhat's theory before, but I still want to just say a few words about this. So I alluded, so I looked at a paraheuric subgroup. I also looked at a special maximal paraheuric subgroup. All of these arise by looking at stabilizers of the action of the group on the Brouhat's building, on its Brouhat's building. So let B of Gf denote the Brouhat's building of G over F. This is a simplicial complex with an action of G of F on it. Now, stabilizers of various facets in this building give rise to various compact open subgroups of G of F. And for example, just to put the groups that we looked at in the split case in context, when G is split, semisimple and semisimply connected, G of OF is the stabilizer of what is called a hyperspatial vertex in the building. And the Iwahori subgroup is the stabilizer of an alcove. And more generally, the subgroups that are of interest to us, the special maximal paraheuric, the mth Moy-Prasad filtration, all of them arise by as finite index subgroups of the stabilizers of facets in the Brouhat's building of G of F. These finite index subgroups are what are called paraheuric subgroups. And with F denoting a facet in the building, let PF denote the corresponding paraheuric subgroup. And as I said earlier, given a facet, Brouhat's have constructed a smooth affine group scheme PF with generic fiber G and whose Hove points exactly recovers this paraheuric subgroup. So then to prove that K mod Km is isomorphic to K prime mod Km prime, first, as I said, one knows how to compare groups now over closed local fields. We need to compare, understand how to compare certain facets in the Brouhat's building of G over F and the corresponding facets in the Brouhat's building of G prime over F prime. And once we do that, we'll denote this map as F going to F prime. One has to study the reduction of this group scheme mod PF to the M and prove that these are isomorphic if the fields are F and F prime are sufficiently close. And now when you take the OF mod PF to the M points, we get the isomorphism that PF mod PF to the power M is isomorphic to the corresponding object over the other field. So that's how that's how this part is generalized. And as I said, there were the other ingredients were essentially the Cartan decomposition and the fact that this is finitely presented. These are already known. And using this, one can generalize this isomorphism to non-split groups. I'll stop here.